Good evening. How is everybody doing tonight? Welcome back to Chem 161. Surprise, surprise, it's more Chapter 3. Wah, 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 wah. Hey, it's this diagram again. Remember how we explained it yesterday? Just to summarize yesterday's lecture, ionization energy is primarily affected by these two quantum mechanical things, n being the principal quantum number, or roughly how far away electrons are from the nucleus, and Z effective, which is the force that is pulling the electrons back towards the nucleus and resisting your attempt to ionize. And as N increases, we can see that ionization energy decreases because it's easier to remove electrons when they are farther away. But as Z effective increases within a period, then the amount of energy that you have to put forth to pull against that nucleus goes way up. Yeah, playing the creepy cadence of Hyrule stuff for Chapter 3 is appropriate, I think. Spooky house, best house, right? Alright. So we're going to be looking at these two terms, and then we talked about these little hiccups right here. So this first hiccup was the transition from S to P. And then this hiccup was the first time electrons paired, and that repulsion makes it easier to ionize something, because the paired electrons in the same orbital are in close enough proximity that when one is being removed, the other one exerts a force on it to repel it. Alright, so let's do the examples here. We didn't really do the examples, I just sort of talked about it and then we ran out of time. So I want you to use quantum mechanics to explain which atom has the higher ionization energy. Which atom is it harder to remove an electron from? Oxygen or sulfur? So do this thing again like we were doing yesterday. So here's our elements, and then we'll go N, Z effective. And you'll fill in the little chart, and then use that chart to help you rationalize which atom is harder to remove an electron from. Okay? And if you have to, draw an electron energy diagram too. So I'm going to give you 2 minutes to think about this. Type in your answer in the chat and your reasoning when you got it. All right. Do we have an answer? Or are we still playing catch up from yesterday's lecture? Which one is harder to remove an electron from? All right, we have an answer. That's the correct answer. It is oxygen. So let's fill in all the information that we have. So N is 2 for oxygen, but it's 3 for sulfur. Now, the wrong Z effectives, unfortunately. So this is the number that you should get. Because if I write the electron configuration for oxygen, oops, it's not 2p6. That's neon. And I calculate Z effective, that would be number of protons, or atomic number, minus the number of shielding core electrons. Now, these are my core electrons right here. So I should get, Z is 8 for oxygen, minus the 2 that I boxed in because those are in the core. That's the effective nuclear charge. Now I'm fighting the same rough force for each of these. You do the same calculation for sulfur and you'll get the same thing. I want to hit erase all, but it'll erase everything up here, and I don't want to do that. Now the question becomes, okay, well, if Z effective is the same, it should be just as easy to ionize them both. Because if we look at Coulomb's law, and I have a 6 plus pulling us against my minus, in both cases, I'm going to have the same E, right? So if these are the same, it's got to come down to this. Which electron is further away, O or S? Which has a valence electron that is farther away? Because if this goes up, this goes down. So the electron that's farther away should be easier to ionize. Oops, I thought that you had the right answer because you wrote O and then a colon, and I was like, oh, that's the right answer. It is O. But you were just listing them off there. So I apologize if I confused you with that. But if I make the distance higher, then the energy of attraction should go down, and it would be easier for me to pull the electron away. But I want to know which one is harder to ionize, so I want the one that is closer. And so that's oxygen. So what we would say here is that if they both have the same Z effective, it comes down to distance. Which electrons are closer to the nucleus? Closer electrons have higher ionization energies. Because remember this diagram here. So if this is N equals 1, N equals 2. Our goal to ionize something is to get our electron from wherever it is up to N equals infinity. Which one of these lines takes more energy to do that? Well, the N equals 2 does. So the ionization of oxygen requires more energy than the ionization of sulfur. And then I like this explanation here because for some reason I have this emote in my sentence. Totally like just that just happened to be there. So now you can and see that. You're welcome. All right. I want you to compare these two. If you live in California, I'm sorry, it's PG&E. We got N and Z effective. I lived in California growing up, so PG&E is basically their Puget Sound electric company, except that California's is incompetent. We do a pretty good job up here in Washington, relatively. California is almost as incompetent as apparently Texas is with their power grid. So, anyway, unrelated. Which of these has the higher ionization energy, phosphorus or germanium? So do the same thing. Write out your N and your Z effective. And then use quantum mechanics to explain which one is harder to remove the electron from. Now, for this specific example, both cases are going to point to a specific atom. So it should be very obvious, like, oh, duh, this one is harder. I'll give you 2 minutes to think about it. I'm trying to move the little like cursor here so that it looks like a nose for my little emote and my frog robot thing. All right, so the answer that you came up with was phosphorus. And that is correct. So let's go over why that is. So if we look at N, phosphorus is in period 3, so its N is 3. Germanium's in the next row down, so that's period 4. Has N equals 4. If I calculate Z effective for phosphorus, you should get 5 plus, and for germanium, it's 4 plus. So if I look at these, I could label them. Okay, lower N is harder to pull from because those electrons are closer to the nucleus, so this is harder. And bigger Z effective is also harder because you're pulling against a bigger force. So there you go. Both facts point towards phosphorus being more difficult to ionize. All right, and that's what my slide is saying here. So we gotta say goodbye to my little robot friend here. All right, so now I have a bunch of pairs of these, and I want you to determine which has the higher ionization energy, which is harder to ionize for each pair. However, one pair is going to give you conflicting information. What I mean is that one of the aspects is going to suggest one element and the other is going to suggest the other. So you won't be able to determine conclusively for one of these. And identifying which pair that is important here. Okay? So tell me which is bigger, and then for one of the pairs, tell me which one it is that you can't identify and why. Okay? So go ahead and do that. We'll go over the answers in about 4 or 5 minutes. Make that little grid. Do the little ends the effective grid every time. It'll help you. All right, 1 or 2 more minutes. We'll go over the answers here. Once you've got some answers, post them in the chat for it. Remember, I want higher ionization energy. All right, let's go over the answers here. So let's look at Lena here. We've got N and Z effective. So lithium is in period 2. Sodium's in period 3. And they both have Z effective of 1. So if we have a tie, not going to help us. So now I got to look at N. Which N represents higher ionization energy? And that's the N where the electron is closer to the nucleus. So that's this one. So lithium is the higher ionization energy because its electrons are closer to the nucleus than sodium's are. And the force to pull them away from the nucleus that you resist is the same. Let's look at rubidium and strontium. Same thing. All right, so I'm going to look at N, and they are in period 1, 2, 3, 4, 5. Both of them are, so that's a tie. That's no use to us. Then I got to calculate their Z effective, and you should get this. Okay, which is harder to pull an electron away from? A force of 1 plus or a force of 2 plus? It's got to be this one. So strontium is the one that's harder to ionize in this case. Because its electrons are being pulled towards it with more force. How about iodine and selenium? This is where we're going to start getting, both of them are different, so we have to compare both things. So iodine is in period 5, and selenium is in period 4. So those aren't the same, so that seems to suggest that selenium is harder. But if I look at Z effective here is 7, and for selenium it's 6. So now this one is suggesting. So this is the impossible one right here, is this one. Because if I look only at principal quantum number n, sure, the electrons in selenium are closer to its nucleus, so that's going to make them harder to pull away. But the force on iodine is going to be more difficult to overcome because it's pulling against a +7 as opposed to pulling against a +6. So these two are difficult to compare, and the only way to really predict would be to do the experiment. For fluorine and sulfur, we can look at their N, and we can look at their Z effective, and in both of these instances, fluorine is the winner. Fluorine is smaller, and it has a higher Z effective. Fluorine is one of the most difficult ions to ionize. Or, I'm sorry, difficult atoms to ionize. And that makes sense, because if I was to remove an electron from fluorine, I would get this, right? You don't really see that. You don't see F+, you see F-. Now, that makes a good segue. What the heck is the opposite of ionization? What if I'm trying to drop electrons into something to make them negative instead? And that would be electron affinity, and that's where we're going to go later on today. But first, before we get to electron affinity, we want to talk about ionizing stuff. We already talked about these exceptions, so I'm not gonna spend more time on these. When we ionize multiple times, we can observe patterns. Every time you ionize something, so if I were to draw a electron diagram here, here's my nucleus. And I'm just going to put electrons floating around here. So these are all pulled toward the nucleus. So if I ionize something and it's gone, the remaining electrons are pulled even tighter. So ionizing past the first electron requires more energy. Oops, I guess I'll just highlight the whole thing, right? So if I wanted to remove a second electron, even if I'm pulling it from the same orbital or even the same sublevel, it takes more energy. Generally, the amount of energy increase is by a factor of like 1.5 to 2. It depends on what exactly you are looking at and what you're changing the Z effective from. So if Z effective is like 2 or something and you pull an electron away, then electrons that are remaining within that shell increase by a factor of how many electrons are left divided by whatever Z effective is. But it will increase, and you'll see that increase if you look at the numbers. But what would happen, and I'm going to erase my diagram here. If I'm ionizing something, here's my nucleus. And so I have this electron up here, and then I have my other electrons over here. I'm going to ionize this one. So it's gone. And then I'm going to try and ionize this one. How much more difficult will that be? Well, not only am I going down to the next level, which means I'm going much closer to the nucleus, I'm also fighting a much higher Z effective. So Z effective up here at the top would have been 1+. This is sodium, by the way. So their Z effective for the top layer would be 11 minus these 10 shielding electrons. But if I'm looking at the Z effective in the n=2 layer for sodium, I still have 11 protons, but now only these are my shielding electrons. So for the Z effective for this layer down here would be way higher. So I'd be fighting off a 9 plus instead of a 1 plus going down to that layer. So not only am I getting closer, but I'm also fighting a way higher Z effective. The result is if you jump down to the next shell from ionizing, the energy will skyrocket. And you are able to see this in the data. So in other words, if you're trying to ionize a core electron, this happens. You observe really large jumps in ionization energy. And I have a picture to show that example here. So here's sodium that we were just looking at. To ionize the first electron, this is how much it takes, 496 kilojoules per mole. Magnesium is a little bit harder, it's 738, and that makes sense, because if I do this, we see that they're both in period 3, but Z effective is roughly 1 or 2. So this number is approximately 2 times this number, right? Because Coulomb's law says, okay, well, if my energy to ionize is you trying to separate these two things at whatever distance, and then you change the atom to become this, that's the same as me just doing that, right? Now, it's not exactly times 2, because remember, the radius decreases ever so slightly when I do that. So there's a bunch of different factors that we have to take into consideration, but primarily, to a first-order approximation, these two factors are important enough. I didn't mean to erase everything. God damn it. That's okay. Anyway, we were comparing these two. So that comparison makes sense. And over here for magnesium, when I ionize the second electron away, it's a little bit harder, by about a factor of 1.5 to 2, like we said before. But if I try and ionize a core electron, this represents a jump from Z effective of +1 to +9. And so these would be Z effective of +2 to +10. And so the jump that you observe is by a huge factor. So that is a huge jump. My ionization energy increased by almost 10 times. Over here, it increased by like 5 or 6 times. So if you see a giant jump in ionization energy, what that means is that that ionization was a core electron. So if you know the number of valence electrons, you know how many electrons you can pull away for relatively low energy. The next one will cost you a lot because it's a core electron. Now, what does that mean for you? Well, I can ask you questions like the one on the page after this, so I guess we'll do these first. So, what I want you to do is I want you to try and rank the atoms on the top in order of increasing ionization energy. So before I was making you pick the smallest one and the largest one out of a pair of 2. Now I want you to do it out of a pair of, or a set of 4. So that just means that you're going to have to make a giant table. Make a Z effective and N table for those. And then I want you to rank these ions in order of increasing ionization energy based on what we just said. So you could consider the ionization of something that has already been ionized as its second ionization energy. Or we could just say, okay, what's the ionization energy of this whole thing in general? So use what you know about them. Okay, so do these problems. We'll go over the answers in about 5 minutes. And then I have more problems for you to try over here. And we'll do that in a second. All right, 1 or 2 more minutes, we'll go over the answers here. All right, let's go over the answers here. So, for all of these, making the giant chart is what you want to do. So we're going to use the same chart for all of these. So I'm going to do calcium, krypton, arsenic, and potassium. Now, if you look at these, you'll notice, oh, they're all in the same period, so they're all going to have the same N, right? It's all going to be 4. 4, 4, 4, 4, 4, 4, 4, 4, 4. So, not super useful, right? That's not going to help you. But now, we can go to Z effective, and we can calculate Z effective for each of these. I don't know where arsenic is. 5? Yeah, 5. And that's really useful. We can arrange these by Z effective. So increasing ionization energy would mean that I want to arrange them from lowest Z effective to highest Z effective. So I'm going to just put my answer bank down here. So potassium is lower than calcium, which is lower than arsenic, which is lower than krypton. Uh-oh, don't do decreasing. Be careful. On the quiz, that will get you no points because Canvas doesn't know. If I was grading these by hand, I would give you half credit, but I can't grade them by hand because there's so goddamn many of them. So be careful, but it's good that you make that mistake here rather than... It's good to make that mistake here rather than on the quiz. All right, so let's erase. We'll go like this. Boop. Zoop. Zoop. And we'll do the next set. I mean, whatever gets you through the class, right? C's make degrees, yeah? If there was one thing that I could tell students, and I wish that they actually believed, it was that nobody gives a shit about your grades when you get to grad school or you're working or whatever. If you get all B's and C's, it's the same as if you got all A's and B's. They're just checking to make sure that you have competence. And in fact, somebody who had B's and C's probably would have done a better job in grad school than I did, personally, if they had different aptitudes and interests. So, like, I really like chemistry, but I hated lab work. You don't want cesium. How come? It's explosive and fun. Nobody wants Cs. I understand that, but it's not that big of a deal. So if I look at all my Z effectives here, they're all 1. So that's not going to be super helpful. So let's look at N. So for sodium, that's 3. For cesium, that is 6, 5, and 4. So the lowest ionization energy will be the one with the highest N, because the electrons are the furthest away. So this would be cesium is less than rubidium, less than potassium, less than sodium. There you go. So there's that one. Now I'll do the last one. And the last one kind of has a combined thing going on for it. So Cl, argon, Br, selenium. So let's look at N. So Cl and argon are in the same period, which is 3. And bromine and selenium are in the same period, which is 4. And then we can look at the effective. So the way that I would do this problem is when you get a problem like this, you need to compare things in pairs. So for example, let's look at these first two. We're going to look at chlorine and argon. So they have the same N, so we're not going to consider N. But we can consider Z effective, right? So, looking at chlorine and argon here, chlorine would be easier to ionize than argon. So chlorine should be less than argon. Because it has a lower Z effective. It takes less energy to pull the electron away. Okay, so we got that pair. Now I'm going to go like this. I'm going to compare two other ones that have something similar. I'm going to compare bromine and selenium. And we can see that, well, selenium has a lower Z effective, so selenium has to be lower than bromine in terms of ionization energy. So we got that. Now let's compare two other ones. I'm going to compare these two because they have the same Z effective. And of these two, bromine is lower than chlorine. So we can write that down too. Why is chlorine lower? Or I'm sorry, why is bromine lower than chlorine? Well, it has a higher N. The electrons are further away. Easier to ionize electrons that are further away. Or in other words, what I could just do is I could do this. We just do that since it's already right there, right? So now all I gotta do is I gotta figure out where selenium goes, right? Because I got these three figured out. And if selenium's less than bromine, well, it's just going to go right in the start there. So that's our order. Selenium must be the lowest, easiest to ionize. Then bromine. Then chlorine. Then argon. So that's a really difficult problem because I'm changing a bunch of variables for you. And the best way to solve those types of problems is to do them two at a time until you have enough information to order them. And there will always be enough information. All right. Let's look at the ions down here. Oh, oops, I didn't erase. these. Actually, we can erase all of this, really, because these are all going to have the same Z effective. So now what we're just doing is we're just going to look at space that is occupied. So if I have a carbon atom and I remove an electron, the radius is going to shrink relative to a regular carbon atom. So let's draw it this way, actually. So here would be my carbon atom with normal number of electrons. If it was positive, it would be smaller because the remaining electrons would get pulled inside. And if it was negative, the electrons would spread out and it would be bigger. Okay. Which is easier to ionize? Electrons that are closer to the nucleus or further from the nucleus? Well, further would be, right? So C minus would be the easiest to ionize, then C, then C plus. And by the same token, sodium plus, sodium 2 plus, and sodium 3 plus, that's the order of their ionization energies too. So it looks like a lot of people got them all right, except sometimes they were backwards. Just because the question was asking for increasing. Yeah, so be careful. All right, here's more questions for you. Explain why cesium is more explosive than sodium when dropped in water. We already talked about that. Let's see if you remember. And then consider the table below. What is the mystery element? Woo! Hint. It's something in period 3. All right, so I'm going to give you 3 minutes to think about that, and then we'll go over the answers for that. And then I think we're due for a break before we start ionization energy, or electron affinity. Yeah. So see you in a bit. All right, so what is this mystery element? I'll give you a hint. Those numbers that are there are sort of a suggestion for the other elements. So, like, sodium gives you a hint. Silicon really doesn't give you much of a hint. What is the mystery element? Who's Al? Or what's AI? No, I'm just kidding. Yeah, it's aluminum. That's totally right. Now, why is it aluminum? How did you come to that conclusion? What made you go, oh yeah, this is definitely aluminum? Because there's something in the data that has to tell you that. So explain how you know. You didn't get much sleep last night, did you? I realize it's 6 p.m. It is pretty late. Hey, I've been doing this for 5 hours now, and I still have another hour to go. So I'm right there with you. But yeah, how did you get aluminum? How did you determine that that was the answer? Not quite where I was going with that. So they are in 3p, so you're going to definitely notice a larger jump between wherever p and s would be. But more specifically, what electron are you taking from which ionization energy that gives you an interesting number that tells you what it is? Look for the big jump. Is there a big jump that tells you, oh, I've ionized a core electron? Because you're on the right track. So if I look right here, so you can see between these two, oops, I have the wrong pen selected. Between these two, that's the big jump, right? Because this is 490, this is 4,500. This is not really a big jump here. This is not really a big jump here. That's a big jump, right? That's like times 5. Whereas these are not even times 2. So the big jump occurs here, which means that the first 3 ionizations must have been valence. And this last one was core, specifically for this element. Yep, perfect. That's right. So these are the valence electrons that were ionized right here. And then that last one was core. So what element has 3 valence electrons and is in period 3? That's important. Because if I didn't say it was in period 3, you could have said boron or gallium or indium or anything in period 3. And, or I'm sorry, in that group. And so the correct answer is aluminum. So just by looking at this data, you can determine what element is present and make a prediction based on where the big jump is. All right, so we're going to take a break, and when we come back, the opposite of all of this, electron affinity. So we'll see you for that in 10 minutes. Oh, I love the Cadence of Hyrule soundtrack. It's so good. But we have to wind it down. Every week I play Zelda Randomizer, like the original NES Zelda. And whoever hosts it has this playing in the background, and it just fits NES Zelda so well. I'm very, very good at Zelda Randomizer. At the end of the quarter, I might show you that. All right, let's talk about the opposite of what we've been talking about. So let's draw our diagram again. That's our favorite diagram. This might be the last time I draw this diagram. So here's the nucleus. And I'm going to actually draw out the orbitals this time. And that's going to be good enough for now. So let's suppose that I have, I don't know, we'll just do that. Let's do carbon. No, the final date shouldn't have to be moved because we will get through all the content. I'm pretty sure. So if ionization energy is me doing this, whoop, whoop, that's ionization energy, right? Moving an electron. Then doing the opposite of that is electron affinity. I'm going to take an electron up here. Oops, wrong pen. And I'm going to let it fall in. There it goes. What's the energy change when that happens? Well, now I'm letting the electron fall in here, so my energy is decreasing. So electron affinity will be negative. So all electron affinities are negative unless, and this is the important exception, unless the electron is ejected. And what that means is that if I try and drop an electron in here, one of two things will happen. One is it will fall into an empty orbital, and then I have a negative electron affinity. Energy is released when I do this. And that makes sense because this is negative and the nucleus is positive, right? These things are going to attract to each other, and energy will be released. But the other thing that could happen is that due to other electrons trying to push this electron away, no, we don't want you, the electron could just be repelled. And so in this case, we say, oh, the electron got ejected. The electron affinity is greater than 0. What that means is that I would have to provide energy to hold the electron in place. And that electron affinity would be positive. Now, it is rare that electron affinity is positive, because why would it be? Dropping electrons in to empty orbitals, as long as the nucleus can hold on to them, it should be negative, and it might be kind of barely negative. But there are some exceptions where it's like, oh, yeah, duh, okay, that makes sense that electron's not going to stick. And that'll be, oh, if I try and put the electron and the only place it can go is too far away, then the nucleus can't see it, and it can't hold on to it. Now, for things like chlorine has a very high Z effective. And if I had my diagram on the screen still, chlorine looks like this. So here's 3s and 3p. There's the nucleus. My electron's going to fall into, so if I have chlorine, I'm going to have an empty space right here. It's going to fall into that. Oh, I just messed that up. Actually, this looks terrible. Hold on. So I'm going to draw it without the boxes here. There we go. My electron's going to fall into this space right here. And this 7+ effective nuclear charge in the nucleus is going to hold it there. So its electron affinity will be very high. Now, I think I have a chart showing these. Do we have a chart in these slides? Let me go find the chart real quick, because it's on OpenStax, and we might as well look at it. Yeah, I don't have the chart on my slide, so give me a second real quick, and we'll find it. because this chart is worth having. Or not having, but at least seeing when I explain this. So I want table of contents, Unit 3, periodic properties, electron affinity. That's first ionization energy. That's second ionization energy. There's electron affinity. That's what I want. All right, so boop. That's way too small. Hold on. All right. You know, I'm going to just make this really big, so I'm going to just cover you guys up for a bit. All right. Actually, you know what I'm going to do? Hold on. I want to draw on this. So we're going to go print screen. I'm going to go into my Photoshop, and we're going to paste. I'll just zoom this in. I print screen the wrong thing, but that's okay. Now you get to see what I see. So this will be fun. There you go. This is what I see on my screen when I'm trying to do this. We don't need to see the bottom part, though. We just care about this part. Okay, so let me make a new layer so I can draw all over this. All right. And so what we notice is that for each of my elements, as I go down... Is this not dry? There we go. Okay. It had to load or something. As I go down a period, electron affinity tends to get a little bit lower and lower and lower and lower. And the reason for that is because if I'm adding to n equals 2, n equals 3, and so on and so forth, the distance that these are from n equals infinity, n equals 2 is the furthest drop down. But n equals 3, I would not drop as far. And 4 would not drop as far as that still. So these numbers get progressively less and less negative as you go down n. And so that's going to be universally true going across, is that as you go down, they tend to get slightly less negative. Now, there are, of course, some exceptions. So there's some weird shit going on here and here, and also here. We're going to talk about those groups specifically. Then, as we go across the periodic table, let me erase all this real quick. As we go across the periodic table, Z effective is increasing. So if I'm dropping an electron down into something that has a Z effective of +1, this is barely going to hold on to it. So I'm going to get very little energy out of it. But if I have this going on here, this is like, yeah, give me the electron. I want it. And so I drop that electron and it basically gets pulled into it like a magnet. So higher Z effective means that I have a higher electron affinity. So if I look at two elements in the same period, their Z effective is 1. Their Z effective, that's 7. Oops, I covered up the number there. And you can see that these are gradually getting higher and higher and higher, with the exceptions in the way that I've indicated. So that's groups 2, 5, and 8. So let's summarize those rules really quickly, and then we'll talk about the exceptions. So over here, we'll summarize. So electron affinity is negative because you're dropping in electrons, and those electrons are attracted to the nucleus. So energy gets released. Now I'm going to say it decreases, but in magnitude. So that means it's going to be less negative as n increases. Because where you are putting the electrons, it falls further if n is smaller. It doesn't fall as far if n is bigger. And then it also increases in magnitude again as Z effective increases, because you have a bigger force that is encouraging the electron to come in, basically. Now, what are these weird exceptions here? So let's go look at the exceptions real quick. So let me clear this. We want to look at these exceptions here. Let's talk about the obvious exception. Let's look at noble gases. Now, neon being negative 30 is actually very strange. And I actually didn't know that until I read this textbook. But apparently neon has an electron affinity that is negative. I would have predicted it to be positive, and here's why. So here's the nucleus. And we're going to draw the electron configuration, for something that is a noble gas. So let's look at neon. So here's what its electronic structure would look like. 1s2, 2s2, 2b6. Here's n equals infinity. And here's the next available empty orbital. If I drop my electron in, it's going to fall down into this spot, right? But what would Z effective be for this electron? Which would be 3s, right? Well, it would be Z minus S core. Well, it's got 10 protons, but it's got all of these electrons are now shielding, and there's 10 electrons there. Z effective for any electron that I try and stick to a noble gas in a new valence shell is nothing. There's effectively no force pulling it inward, right? So you have to provide that force to hold the electron in there most of the time. And why this is like this, I actually don't know why this one is negative. I would have predicted it to be positive, but it's a weird sort of situation. I don't know. But for elements in 8A, Z effective is 0. So the electron really just doesn't stick. So we'll add that down here. Here's our exceptions. Okay. Now let's look at group 5. So that's going to be something like nitrogen. So let's erase. And so nitrogen is going to look like this. Here's what nitrogen looks like. And any element that is in group 5A will have 3 unpaired electrons that are already there. I'm going to drop an electron in, and it's going to fall into the first available spot, which is any of these 2p orbitals. What specifically happens, do you think, that would allow my electron affinity to not really want to take? Like, why would the electrons not want to have another electron in there? And then, so Z effective for here is 5+, just as a reference. What do you think is going to be the driving force of resisting the electron and ejecting it? It is electron repulsion. Specifically, what event, though? Can you be more specific? You're definitely on the right track. Yeah, you're trying to pair electrons. So in order to do an electron affinity for nitrogen, I have to put an electron in an orbital that already has electrons in it, right? Now, if Z effective was bigger, I could probably manage that, because oxygen does just fine. But with nitrogen, 5+ isn't enough to really start accepting paired electrons that are this distance from the nucleus. And so what ends up happening is nitrogen goes, I'd rather not. And the electron doesn't stick. And you'll notice that in all of the elements in group 5, having a Z effective of 5 is not really enough, because the previous electron affinities are all higher in magnitude. Remember, electron affinity should be increasing as we're moving to higher and higher Z effectives, but this exception occurs in group 5A, where I have to pair an electron, and that electron-electron repulsion in that same orbital makes all of these go way down. It's kind of like how ionization energy goes down when I try and ionize oxygen, because oxygen already has a paired electron, and that paired electron helps me push the one that's paired away. Here, I'm trying to pair an electron. There doesn't exist one yet, but doing so makes it difficult. So we'll go add that to our exceptions too. So group 5A, paired electron reduces magnitude of electron affinity. And we'll say paired electron repulsion, because specifically it is, we are putting two electrons together, and that repulsion exactly equals the amount of energy that we would be gaining for nitrogen. And it is really weird that you land exactly on 0. So a previous textbook that I had, it only listed it didn't have positive numbers. It only had the negative value, or it said greater than 0. And for nitrogen, it was greater than 0. So I've always learned, oh, it's positive. But according to this data that they have, it's 0. I'm like, whoa, really? It's 0? And that's just one sig fig. So, it could be positive 0.7 or something like that. But it's not exactly 0. That's not a definition or anything. Okay, last but not least, let's look at group 2A. I got to get that on the screen here. All right, so group 2A would just look like this. Let me get rid of my repulsion right there. Here's group 2A, and I'm going to drop this electron into the 2p orbital with my Z effective of 2+. Well, 2s and 2p are very different in energy, as we've learned. P orbitals are higher in energy than s. So this p orbital being higher in energy means that it's just not close enough to the nucleus that this 2+ can hold on to it. And so what ends up happening is that this electron is just like, I don't even see the nucleus, and it just leaves. So it requires a lot of energy to get electrons to stick to elements in group 2A, because 2p is just higher in energy than 2s by a significant amount. The other reason is that because s orbitals are quite small, you're trying to cram an extra electron into an area that is very small. And so those repulsions will be quite significant as well. But the primary reason that we're going to go with is that for anything in group 2A, the p orbital is too high in energy for nucleus with Z effective 2+ to stick. Or not to stick, sorry. I was thinking of the electron. To hold electron. So there you go. So that is the entire chart for electron affinity explained. So to summarize, remember, and the trends are more important than the exceptions, but you should recognize where the exceptions are. Electron affinities are negative, and they are based off of how much energy you get when you drop the electron from n equals infinity. So it's like holding it above the atom and just letting it go. It falls down. The further it falls, the more energy is released. If it doesn't fall very far, less energy is released. So n determines this primarily. The other factor is Z effective. The higher Z effective is, the more that electron is going to be attracted to the nucleus that it's falling toward, and the higher the magnitude the electron affinity will be. And then the exceptions are groups 8, 5, and 2 for the reasons that are on the screen that we just talked about. All right. So my slides talk... Oops, I got to get rid of this thing. My slide talks about that. So here's the first point, which we talked about. So I'm writing it here in absolute values here. So I wrote the words more positive, whereas on the Photoshop I wrote less negative or less magnitude negative. And for that, it's because as n increases, electrons don't fall as far. As Z effective increases, your electrons are attracted closer to the nucleus. And remember, as electrons are attracted to the nucleus, they tend to get closer, right? How atoms get smaller as the effective increases. So this effect also occurs too. So the electrons are falling further. But the effect of the nucleus pulling those electrons in is also relevant to know too. And then we talked about the 2A exceptions. And then on the next slide is 5A and 8A. So let's do these examples together. Let's figure out which has a more negative electron affinity. So we're going to look at elements that are in... We're just going to look at elements that are next to each other is what I want to say. But we're going to want to know what groups these fall into. So this is group 3A, and this is group 4A. And this would be period 2. So if they're in the same N, we could still do this sort of thing here. So they have the same N, so this is not going to really affect anything, so we'll just cross it out. But Z effective for boron is 3+, and this is 4+, and none of these are exceptions. That's why I'm labeling them. So we would say, okay, they're falling the same distance, so they both... it's a wash here. But this is a stronger attraction, so carbon should have the more negative electron affinity. And if we look at the chart, and I'll call up the chart here, boop, you can see that, yeah, carbon is way more negative than boron. Oh, you can't see my cursor. There we go. Boop. All right, let's do the next one. Let's look at sodium and potassium. So these are both group 1A. Those aren't exceptions, so... Let's look at the wash stuff. We don't care about that. They're in period... What is sodium? Sodium's in period 3. And potassium's in period 4. Which one falls further? It'll have the more negative EA. That's sodium. So sodium has lower EA. I don't want to write lower. More negative. Because the electron falls further from n equals infinity. All right, so let's circle our answers here. So that was that one and that one. Okay. Now, for bromine and krypton, if I write down their groups, you should immediately go, oh, exception! And so the other one wins, right? Same thing down here, 4A and 5A. Oh, exception! This one must have the more negative. So exceptions are always losers. They are always a more positive EA. And then same thing down here. Here's 2A and 3A. Ah, exception! This is the winner. So your job for electron affinity really is to remember, how does N affect it? How does Z effective affect it? And then what are the exceptions? 8A, 5A, and 2A. And can you explain those exceptions? If you can, you're in great shape. All right. Are there any questions about electron affinity before we go on to the next thing? How much time do we have anyway? Oh, we have 10 minutes. Okay. All right. So I told you there'd be a special announcement, and that special announcement is this. That is the end of quantum mechanics. That's it. No more quantum mechanics. We're all done. You survived. There's a lot less enthusiasm than I thought. Maybe it's still reaching out to you in the past. I don't know. But future me is very excited. Okay, there we go. That's better. Hooray. That's it. There's no more quantum mechanics. You don't have to worry about Z effective, N, L, M sub L, M sub S. That was Mario World for the SNES. I slowed it down a little bit. Or I pitch lowered it. And then I put a applause track over it. I did that years ago for something, and I just kept the sound file. And now I use it for teaching. All right. You know what we should do? We should do easy shit. Let's do easy shit. Let's talk about the periodic table. Remember this guy? This is Dimitri Mendeleev. So, Dimitri Mendeleev noticed a lot of these periodic properties and decided, you know what I'm going to do? I'm going to put them all on a table and arrange them such that everything lines up to match observed properties. So, for example, if we go back to electron affinity, I just told you we weren't going to deal with that shit anymore, but if we go back to electron affinity, if we didn't have the chart, and you notice that randomly every X element resisted electrons, like the electrons got ejected instead, you might be inclined to think, oh, there might be a pattern here. What is that pattern? So what Dimitri Mendeleev did was he stacked all the elements that did that in a column. And he did that with other regular patterns, such as like, oh, these elements have this many valence electrons. I'm going to stack them all together. And so what he ended up doing was he created the basis of the periodic table. Now, just in case you've never seen Dimitri Mendeleev's actual periodic table, let me find that. Mendeleev periodic table. I always misspell Mendeleev because it has two E's in it, so I had to pronounce it Mendeleev. All right, here's what it looks like. This is what his periodic table looked like when he was working on it. Oops, that's a little too big. I like how the periodic table says known to ancients on there. There you go. So this is what his table looked like. And you can see that it's pretty similar to what we have, right? With the exception that, like, most of the elements at the top there, so like beryllium through fluorine, that all got shoved over to the right side. And the reason for that is because we've done more work on p electrons and stuff like that, so we could separate all that out. But these were all the properties and traits that he could observe. And he said, oh, okay, all these elements react pretty similarly. I'm going to stack them all in the same column. Now, there were some weird oddities that went on, and you can see that, like, down here... Oops, I gotta click on the page here. Down here, potassium and copper both do not explode when you drop them in water. In fact, copper's pretty inert, right? But copper does have some similarities. For example, it has one valence electron. So does silver and so does gold. Remember the half-filled and totally filled exceptions. You end up with 4s1, or 5, or you end up with s1 doing that. So there were observations that were consistent with that. So all of the information that Mendeleev pulled together, he put into that periodic table, and then we refined it, and we got this periodic table. And so this periodic table is what we use today, And we're already up to element 118 here. I don't know about element 119, what the work is on that. I have been using this terminology all along. I didn't realize that we hadn't actually formally introduced it. But yeah, if you don't know what a group is by now, groups are columns on the periodic table. So I very much apologize if I didn't say, oh, a group is a column on the periodic table. And then rows going across are periods, so that's what I was referring to. Remember that periods correspond to your valence shell, N. And then elements in the same group have the same number of valence electrons. Yeah, nothing really exciting here. Here's some names. You probably know these names from Chem 140. I'm going to highlight the names that I want you to know. Those are the important ones. I want to highlight this one because I personally worked in a lab that did lanthanide and actinide chemistry. But to be honest, nobody gives a shit about them. So I really shouldn't. Those are the important groups to know. I personally am a lanthanide actinide chemist. I specifically did chemistry with uranium. Is it radioactive? Yes. It is very, very mildly radioactive. The uranium I worked with, uranium-238. But I didn't do nuclear chemistry with it. I did actual chemistry. So, like, I reacted it with, like, hydrocarbons. And I got a crystal structure out of something. So I've crystallized a uranium compound. And if you type in my name and you type in uranium, you might find my published article. I am a published chemist. I did barely any work on the paper. I did the crystallization. The other grad student wrote the paper, and I got credit for it. So hooray. Grad school is kind of silly. So know what these groups are. The group names are. So group 1 is the alkali metals. Group 2 is the alkaline earth metals. Group 17 is halogens, and group 18 is noble gases. I do not give a shit about chalcogens, and I literally had never heard of the word pnictogens until I got this textbook, which was probably a year and a half ago to 2 years ago. I was like, wow, that group has a name? I had no idea, because nobody uses it. But halogens are common enough, so you should know that. Do we want to do this exercise? This is busy work. Let me just see. Not really, so. Are we comfortable with determining the number, the group number and period number and category of these elements? Like, can we skip this? Can you do that? I think you're okay. How much bigger do you think the periodic table will get? That's a really good question. I personally think it will be a long time before 119 appears. And so the reason for that is because we would need to have a 9s orbital for element 1. Is it 9s? 1, 2, 3, 4, 5, 6, 7. It'd be 8s, sorry. We'd have to have an 8s orbital. And an 8s orbital would just be so big. Like, it would be that electron would be so far away from the nucleus. I can't imagine it being stable. And then even more importantly, element 121 is the first element. So element 121, whatever it ends up being called, will have an electron configuration that will actually include a 5G electron. So G electrons are a thing. This would be for n equals 5, L could be 0 through 4, and 4 corresponds to G. So that is a thing. It's just it never shows up until element 121. So we would actually have to start an entirely new thing on the periodic table if we got to element 121. It would go below the lanthanides and actinides, which would be really cool. I don't think it's going to happen, though. And I just want to finish this section before we call it a night here. So this last little bit is, hey, what are metals? Metals are defined by these properties. Metals conduct electricity really well, and they conduct heat really well. The other thing you can do with a metal is that they tend to resist breakage. So if you hit a metal with a hammer, it has a property called malleability. It will just change shape. It will become thinner and its surface area will increase. What ductile means is that if you pull on it long enough or with enough force, all you do is you make it into a thinner and thinner wire. And so this is how you draw stuff into wires. You basically take a piece of metal and you pull on it from both ends, and the once you've made it into a cylinder, you just keep pulling until it is the gauge that you want. So this is how you make copper wire: is you get it into a cylinder and then just tug on it with mechanical help until you get the thinness that you want for whatever electrical work you're doing, because most electrical wire is copper. And then the last property of metals is that they're shiny. Now, we don't really talk about this in this class, but for what metals, the reason that metals are shiny is because all of their electrons equals whatever. All of their electrons are kind of in the same layer, so these are the d electrons. And what ends up happening is that there is a bunch of empty orbitals above these that these electrons can jump up to. And this is called the conduction band. And when you apply a current to a metal, these electrons go up into this, and then they're mobile, and they can go where they want to. And all the electrons move. This is how you get a current. But if you don't apply a current to this, and you let light do this, well, the light causes the electron to go up into the conduction band, and then the electron falls right back down, and you get that light right back. So when light shines on a metal, the electrons just go up and go back down, and the light is returned in all directions, and we interpret that as luster. And so that's why Bender is on here, because Bender's quote is "bite my shiny metal ass." So also Bender is just really cool. He's made of metal. He's a metal. He's shiny. All right. Now, elements that have none of these... Oh, it just popped up. What kinds of properties would something of the 5G orbital have? Now, I think I'm specially qualified to answer this question because I've dealt with F orbitals, and elements with F orbitals do almost nothing. Well, specifically, the F orbitals don't do anything. And the reason for that is because the orbitals are too small. So, like, the 4F orbital in a lanthanide doesn't quite get out far enough. And the D and P and S orbitals for the higher valence shells are just so much bigger that they're the valence electrons, and they're what interact with other things. So if you ask me what kind of properties would something with 5G orbitals have, my expected answer would be absolutely none that you could do anything with. Like, it'd be a curiosity. Thank you for asking that question, because I feel like, wow, my degree actually got put to use there. I'm the only person at Everett Community College that could probably answer that question. That makes me feel pretty good, actually. All right, what's a nonmetal? Nonmetals have none of these properties. So, nonmetals do not conduct electricity. They do not conduct heat well. They're not shiny. If you hit them, they shatter because they don't have metallic bonds. And then finally, a semi-metal or a metalloid is something that sort of has some of these properties, but not all of them. So, for example, silicon has adequate thermal conductivity and has adequate electrical conductivity. And that's good for computers because we do not want our computer to be completely conductive. If it were, we couldn't control electrons as they flow through logic gates. So we want there to be some resistance so that we can like carve a path for our electrons to move through the circuits that we design. So metalloids are really useful as the sort of like Goldilocks just right of the periodic table for making semiconductors and circuit boards and stuff like that. So that's why all of our computer chips and graphics cards and motherboards are made of silicon wafers. because they have some of these properties of metal that we can exploit, but they don't have all of them that would make them uncontrollable. On the periodic table is this zigzag right here. Not every periodic table has this, unfortunately, but those that do, that line is called the metal non-metal line. Yeah, we are running out of silicon, I've heard, which is really bad. Like, I don't even know what the answer to that's going to be. Like, there's not an alternative. I mean, the alternative would be to recycle old stuff, and that is actually a big market. It's not going to happen in my lifetime, though, so I don't know about 2100, but I hope that people find a source of silicon. Maybe start, like, asteroid mining. Anyway, this is the metal non-metal line. Everything that touches the metal non-metal line is a metalloid, with two exceptions, aluminum and polonium. This is astatine. It's radioactive, so nobody gives a shit. And you can remember this by remembering the dog food Alpo. But really, aluminum is the big important one. Now, the cars being delayed because they can't get silicon chips is actually a manufacturing slowdown due to the pandemic. Because car sales went way down at the start of the pandemic, demand for those chips went way down, so the production went way down. But now the demand is much higher, they need to make up for that delay, and the system hasn't caught up yet. So I know that chips are scarce because production was low due to the pandemic for quite a while. So hopefully that will be resolved, but I do know that there is an overall silicon shortage that is coming up. Like, silicon is abundant naturally. Like, it's just sand. You go to the beach and you get some, right? You just harvest it off the ocean floor if you really wanted to. But that takes effort. And do we want to put in effort? I don't know. Yeah, me too. When I build a new computer, I'm thinking about building a new computer. Not really, because my computer's still pretty good. But, like, good luck getting a 3080, right? Metallic character, as you go left to right, metallic properties decrease, so I have it written the opposite way on here. So as you move right to left, things become more metallic. And same thing if you go top to bottom, they become more metallic. Yay, that's it. That's all I want to talk about. So, pretty pictures, you can see that things get more metallic. Like, I don't even know why this section is in Chapter 3. Like, compared to all the shit that we did in the previous section, and now it's like, here's some pictures of metals. Like, hooray, we're back to the old Chem 161. Guess what? We're going to finish Chapter 3 next week. And then we'll be done with it forever. And then you'll no longer have to speak of it until, like, Exam 2 and then the final. So you have to speak of it a few more times, I guess. But you did it. You made it to the end. Almost. Next week, there will be a quiz that's posted for Unit 3. We are going to have a lecture on Wednesday. We are going to have a lecture on Monday where I finish Chapter 3 instead of a QA, just because I want to make sure we get through Chapter 4. So Monday will be a lecture day and not just a lab Q&A, because there is no lab to talk about yet. You're going to be working on lab number 4. And if you have any questions, I'll still answer them. But come in on Monday's lecture prepared to just take notes for the remainder of Chapter 3 and then the start of Chapter 4. I can't believe it. I'm saying the start of Chapter 4. That feels really nice. Have a good weekend.